It's a pleasure now to welcome our next speakers, Dr. Paul Spudis from the Lunar and Planetary Institute in Houston, whose talk is here. Okay. You found out how to get it full screen.
Yes.
So Paul has been a long-standing advocate, probably one of the world's strongest advocates for using the moon and leveraging the resources of the moon, both for science and for exploration. And he'll tell us about it now. And if we could dim the lights a little bit.
Yes, thank you, Ian. It's a pleasure to be here today. I want to talk about the moon, but from a different perspective than I usually talk about it, and that you probably heard about it. I think that one of the interesting things we found in the last decade of lunar exploration is that the moon is actually an asset. It's a useful asset, and that's the theme of my talk this morning. I always talk about the value of the moon in terms of three principal attributes. It's close, and what that means is, effectively, we can always and easily access it. We can get to the moon any time of the day. There's no specific launch window. It's constantly accessible. It's only 400,000 kilometers away, so at most it's a 2 to 3 day trip. You can go longer trips to save energy, but in effect, it's the closest celestial object that we have, and it also has the ability for us to set up a continuous loop of access, so we can go to the moon and from the moon at all times. It's interesting, and it's a natural laboratory for planetary science. It's a platform for observing the universe, and it's a unique environmental laboratory for materials and biological science. A lot of the biological questions in space medicine, for example, need to be addressed in terms of fractional gravities that we don't have available on the ISS. But the area I'm going to focus on this morning is the last part. It's useful. It's useful in two senses. It's useful in the sense that it has the material and energy resources we need to begin the development of space, not just the exploration, but the commercial and practical development of space. But what's more, these resources are in a form that's easily usable. They're accessible and usable. So I want to talk, the reason the moon is so interesting in this regard is because of the unique environment of the lunar poles. And that environment is caused by the obliquity of the moon. The obliquity of the moon is only 1.5 degrees, as opposed to the Earth's obliquity of 23.5 degrees. And what that means is that at the poles, the sun is always on the horizon. Now, if the moon is perfectly smooth during the course of a lunar day, of a 708-hour rotation, you would see the sun move slightly above and slightly below the horizon. But because the moon has topography, there are areas that get no sunlight at all. They're called permanently shadowed regions. And there are areas that potentially might get constant sunlight. And I call them quasi-permanent sunlight areas. I call it quasi because they're not totally permanent. We have found no place on the moon that has permanent sunlight, but we found multiple places where they're illuminated for greater than 90% of the year. The areas of constant sunlight are useful because you can generate electrical power via solar photovoltaics, but also they're thermally benign. The temperature of the surface in these areas is about minus 50 centigrade, and it varies plus or minus 10 degrees from that. Whereas opposed on the equator, you have a 100 C to minus 150 C temperature swing over the course of a lunar day. The areas of permanent darkness get no sunlight whatsoever and are only illuminated by the 3 Kelvin background radiation of the universe, and in fact they are very cold. We have found areas that are as cold as 25 K, which is actually colder than the surface temperature of Pluto. The Earth moves up and down the horizon, and that's dictated primarily by the inclination of the moon's orbital plane to the Earth, which is 5.5 degrees. So sometimes the Earth is above the horizon on the pole, sometimes it's below the horizon. I mentioned the lighting studies, and from Lunar Reconnaissance Orbiter, we've made a very comprehensive and detailed study of the illuminated areas. There are quasi-permanent sunlight areas at both poles. In fact, but they vary in the length, terms of their quality, in terms of the length of time you actually see the moon. Now, these images are composites of wide-angle camera images showing the areas that are permanently darkness are black, and the areas that are in quasi-permanent sunlight are white. The two red arrows point to the two best areas I found at both poles. The one at the North Pole is near the crater Whipple, which is on the rim of the crater Perry. That gets sunlight for about 92% of the lunar year. The area pointing at the rim of the crater Shackleton, which, by the way, the pole of the moon is about the 10 o'clock position on that image. So this is very close to the South Pole, gets illumination for about 95% of the lunar year. In addition, some of the areas around there are illuminated when these areas are in eclipse. So in effect, if you put an array of solar power generation on these adjacent peaks, you could be in permanent sunlight. Each one would be in sunlight at some point of the year. This is an example of some of the Diviner thermal data. Diviner was a thermal emission spectrometer that measured the surface temperatures. Anything on this map that's cooler color than yellow, ice is stable on the surface. 104 Kelvin, ice is stable on the lunar surface. And in fact, 10 centimeters below the surface, ice is stable up to about 120 K. So in fact, what this shows is there are large areas near the poles of the moon that are in significantly cold to retain large quantities of water, and effectively this is for geologic time. So if a water molecule gets into a cold trap, there's no known physical process to get it out again. The only way you could get one out is to have a micrometeorite impact that kicked up a vapor cloud. If the vapor cloud came into sunlight, it would be subject to the stripping processes that water molecules are. Otherwise, it recondenses and falls back down into the cold trap. Now, I want to talk a little bit about the radar data. I had an instrument on 2 missions to the moon. One was the Indian Chandrayaan-1 mission, which orbited in 2008. And then we also had an advanced version of that radar instrument on Lunar Reconnaissance Orbiter called Mini-RF. And radar senses ice by looking at the diffuse reflection patterns around the phase angle. And we look at something called circular polarization ratio, which is merely the ratio of polarized transmitted RF in sense of that sent to that received. So in effect, an area that's perfectly smooth has low CPR. If I transmit a right circular polarized pulse, I get a polarization inversion. I get a left circular polarized pulse back. However, if I get a dual bounce, like you see up there with that rocky surface, it can bounce twice, I can get the same sense back. That means that rough areas with rock have high CPR, high circular polarization. The other way that you can get enhanced CPR is through the coherent backscatter effect. And in effect, ice is a transparent media to RF. So the RF penetrates, it's multiply scattered, but it comes in and along the same identical path length, so you get double the power back. So a pure ice deposit would have a CPR of 2, and that's at the phase angle. That is, when you transmit and receive along the same line of sight, monostatic, you're looking at 0 phase. Now this phase relation is shown in this graph here, where you see water ice has a very strong opposition effect. As I get closer and closer to 0 phase, I see a very great brightening in the CPR, whereas rock falls off much more gradually. So what do we see when we actually look at the craters of the moon? The top view shows the crater Main L, which is a fresh impact crater. And what you'll see in the colored image is that yellow is high CPR. You see high CPR associated with the interior and the exterior of that crater. Now this crater is in partial sunlight over the course of a lunar day, and this is a typical lunar crater. The amounts of CPR that you see inside the crater are identical to those that you see outside the crater. However, we found in the course of this investigation a number of craters that, especially near the poles, we call anomalous, that have high CPR inside their interiors but low CPR outside their interiors. This particular one here is Rozhdestvensky N in 2 wavelengths, S-band at the top, which is about 12 centimeters, and X-band, which is about 5.6 centimeters. And what you see is you see high CPR inside the crater, but low CPR outside. Now, what's the significance of that? This crater is in permanent darkness. It is covered by, it has a very cold interior. So in effect, we interpreted this asymmetry in the CPR pattern as indicative of the presence of water ice. When you map these anomalous craters all over the moon, it's clear that they're not all due to water ice because some of them occur at mid-latitudes as well. But if you look at the distribution map, you'll find the vast bulk of them in green occur within 10 degrees of the lunar pole. So at least some of them are probably related to the presence of water ice in them. And when we compare this with other data, these maps on the bottom show on the left permanent shadow, the neutron spectrometer data from Lunar Prospector, and finally the CPR anomalous craters. There's a reasonably good correlation between these 3 data sets, suggesting in fact that we are measuring the presence of water ice in these permanently dark craters. One of the biggest surprises of exploration in the last 10 years is that the moon has a hydrosphere, if I can call it that water occurs in quantity on the moon, and it occurs in a variety of forms. The M-cube data, which is also on Chandrayaan, that was an experiment flown by JPL, shows that as you look at the absorption feature, the 3-micron absorption band for water, it increases in strength as you go to the poles, from about 65 degrees poleward at both poles. And in fact, it's highest at the poles, and this correlates with mean surface temperature. The cooler the temperature, the more water and hydroxyl absorption you observe. In addition, we found from the L-Cross experiment, we collided a empty Centaur upper stage with the regolith in the floor of the crater Cabeus, and we found an ejecta plume that contained anywhere from 5 to 10 weight % water. And this is now confirmed. We not only saw water vapor from that impact, but we saw water ice particles as well. I'll talk about some more indicators of water later this afternoon when I talk in the ordinary session. But there were other experiments, including an exospheric experiment from the Moon Impact Probe on Chandrayaan, which measured a water cloud over the South Pole, and also the LAMP experiment, which measured UV spectra and determined surface frost on the floors of several polar craters. And then finally, the radar data in aggregate, when you look at all the craters and you integrate them all together as an estimate of the ice volume, I get several hundreds of millions to billions of metric tons of ice at each pole. And it varies in quantity spatially on kilometer to decameter scales. So, having covered the background, this is sort of what the moon has to offer. Why is water so important? Well, water is one of the most useful substances you can find in space. It's very heavy, so it costs a lot to, it's effectively 6 kilograms per gallon to launch it off the surface of the Earth. And it costs a lot of money to launch something from the surface of the Earth. If you can find it in space, you've saved a lot of money. It's a source of life support consumables. You can drink it, you can use it for food preparation, you can use it for sanitary purposes, you can shield your habitat with it to protect you from cosmic radiation. It's an extremely useful substance for that. It is a media of energy storage because you can use rechargeable fuel cells to combine hydrogen and oxygen during eclipse to generate electricity. When the sun comes out, you can crack that water back into its component gases and store it for use later on. So in effect, you can be on the moon permanently through a combination of solar arrays and reusable fuel cells. And finally, and most importantly, it is a source of propellant. And hydrogen oxygen is the most powerful chemical rocket propellant known. And with billions of tons available on the moon, we can learn to use a different paradigm of spaceflight. And a different paradigm is more space-based, less launch from the Earth, more based in space, reusable systems that get refueled and reused rather than discarded, and finally, permanence, both human and robotic, deeper and deeper into the solar system. So what's the goal of all this? What am I aiming at? I want to extend human reach beyond LEO by creating a permanent spacefaring infrastructure. And effectively, what I envision is a series of nodes from which you can depart to and from to other locations. For example, you might have a node in low Earth orbit where you can use as a jumping off point to go deeper into space, but also as a place to come back to return to Earth. That way we keep our launch infrastructure solely focused on access to LEO and back. We don't have to worry about deep space because that'll be taken care of by the materials you extract from the moon to fuel your deep space system. You can achieve a system like this through small incremental steps. And this is an important point to realize. One of the big problems that the United States has right now, convincing people that the Mars mission is doable, is the fact that it is a huge money pill to swallow. And in fact, you have to ramp up funding in terms of tens of billions of dollars per year to even make this feasible. So instead, if you could build an infrastructure gradually and incrementally for much lower cost at a much lower rate of expenditure, larger costs might be much more acceptable because you're building stuff up gradually. So you want to use the moon as a logistics depot, in effect, and do this under a reasonable budget envelope. The way you do this is you make schedule a free variable. You don't set a deadline, moon based by a decade or it's a failure. You basically set a strategic horizon. You identify the small pieces that allow you to get there, and then you gradually and incrementally put them all together. So what does this mean for the architecture? What does this mean for the way we do spaceflight? I contend that it kind of changes our approach. It should certainly change our attitude to the way we do things. First of all, I want to use robotic flights to do practical work rather than just explore. So the architecture that we've come up with as an example uses robotic assets first that go to the moon, prospect for water, put in the initial machines to start extracting and storing the water, and then people come when a usable facility is established and ready. Now, this is where the proximity of the moon comes in handy, because the moon is so close, you can teleoperate machines on the moon, whereas you can only teleoperate, you can only do very remote, cumbersome operations with robots on the planets because of the very long round-trip light times. On the moon, it's 3 seconds round trip, so you can actually do a lot of the work with robotic assets on the moon controlled from the Earth. There's a commonality of hardware and systems between human and robotic systems. When you build a lander, there's no sense in building 18 different landers. You build a couple of standard landers of different size classes, and you use those for all your missions. You locate your facility near the best high-grade lunar resources you can find. I think we can identify these in a preliminary manner now. I certainly want to fly prospecting missions to confirm those before we start. And finally, you build up infrastructure at a single location. I think one of the big problems that we had with the Constellation program that was canceled was its emphasis on sortie missions. And the idea was to go to a bunch of different places all over the lunar globe. The problem with that is if you do that, you can't build up enough infrastructure at a single spot to really do anything productively. So about 5 years ago, I published a paper on this with my colleague Tony Lavoie at NASA Marshall, and we described a lunar return architecture. And I don't offer this as the way to go back to the moon. I offer it as a way to go back to the moon. And our bounding condition was taken, believe it or not, from the Augustine report, which is in 2009. They concluded that a return to the moon was unaffordable. And we didn't like that conclusion, so we wanted to show that they were wrong. So we adopted their boundary condition, which was $7 billion per year spent on, quote, exploration activities. So in effect, you see I'm changing the game 2 ways. One is I'm keeping this under the agreed bounding condition that Augustine laid out, which is still pretty much what we spend on that, by the way. But I'm also blurring the line between human and robotic. I'm combining them into one program because the robotic missions I advocate actually lead to long-term human presence. We basically were launch vehicle agnostic. Any launch vehicle that's available we'll use. For the purposes of this exercise, we used the standard available Atlas Vs. If you can get cheaper launch, so much the better. It just makes our bottom line look better. And we assumed only 10% ice. I think there are many places near the poles from the radar data that are nearly pure ice. And they're not very big, but they certainly exist. But we assumed that basically a regolith with 10 weight percent ice would do the job. And we spend at that rate, and how long would it take to build a workable outpost, and then what would you have at the end of that process? So here's how you do this. Basically, you lay out a plan where you first install the infrastructure you're going to need, and that includes the communications and navigation system. The topography near the poles is very rough. You have big peaks, you have deep craters. You want to be able to communicate with all your assets at all times. The way to do that is to have a network of communication satellites in high elliptical orbits, polar orbits around the moon, so there's always a ComSat available for use to communicate. In addition, you can install in these ultra-stable oscillators and basically extend Earth GPS out to the lunar distance. So all navigation through cislunar space becomes part of one GPS system that you can access anywhere in cislunar space. You send prospecting rovers to go and look for the highest quality deposits. We can identify where these are likely to occur now with the existing data, but we need ground truth because we're not absolutely certain not only what the grade of the ore is there and how much water there is, but what the physical nature of the polar regolith is. There's some intriguing evidence from the data that the polar regolith might have physical properties slightly different than we expect. And so what we want to do is to go there and determine for sure that we can do this, that we can dig up this material. We do an ISRU demo where we dig up feedstock, heat it, extract the water, and store it. So an end-to-end system of what you plan to do eventually. Now next comes a stage where we actually start the mining. And I always like to say this is the part I leave as an exercise for the student, but in fact there's a serious question here, and that is at what level is continuous processing possible? Because there's a huge payoff difference between batch processing versus continuous processing. With continuous processing, you constantly dig up feedstock, you deliver it to the processing ovens, you extract the water, you dump the waste, you store the water. With batch processing, you do that serially. So you do each step, and then you go back to square one. Very inefficient, and fundamentally, you can't really pay your way that way. You need to develop you need to develop continuous processing as soon as possible. It's very easy to store the water, by the way. All you have to do is put it in solid form, put it in the cold traps. It'll stay there forever. It ain't going anywhere. Next, we need to work on electrolysis units to crack the water into its component gases. A variety of supporting equipment includes different classes of robotic landers. The power plants we envision as landers that land and extend a vertical shade that's articulated on a vertical axis. So as the sun moves around the horizon, you can track the sun constantly to get the maximum solar output. We need a variety of materials fabricators using 3D printers to make different piece parts. And in effect, you're going to place the outpost on the moon robotically. Finally, there are some space-based assets. We use a LEO depot to fuel our departure stage. And we actually have a fuel depot in low lunar orbit where the lander goes back and forth to that. And in effect, what this does is this creates a complete transportation system. Once we've placed this lunar base, and by the way, we costed this out at $7 billion per year for 16 years to get a completely operational outpost. And that first cost includes at least the first 3 human missions. And then afterwards, crews of 4 come for tours of 90 days each. So it's half time occupied by people, half time occupied by robots. And what we calculated to the point where we're producing 150 metric tons of water per year, and that's break even. Any water that you produce over that is available for sale. So you can export it from the moon, you can sell it to any customer that you might have in cislunar space. So in effect, what have we done? Well, we spent approximately $87 billion, but we've also created a permanent space-based transportation system, a system fueled by the mining and harvesting of lunar water. So, the advantage of this program is that you can actually implement this in an affordable manner. You can achieve it because you're biting off small chunks one at a time. Each step adds a capability so the individual pieces work together as a whole. So each piece might be small, but it operates together as a system of systems. Now, once you've got this established, then the entire volume of cislunar space is accessible. Not just the lunar surface, but all of cislunar. To give you an example of how you might use that, suppose you could build a communications complex in GEO that was the size of the ISS. Well, in one fell swoop, you've completely made the terrestrial cell phone network obsolete because you can effectively access any point on the hemisphere that this thing is stationed over using this kind of communications complex. So there's all kinds of possibilities to industrialize and create new capabilities in cislunar space by going to the moon and using its assets. So, in addition, a system that can access cislunar space can also go to the planets. So we obtain a foothold on another world, and more importantly, a place where humans can go not just for temporary visits, but permanently. So what kind of space program do you want? And unfortunately, right now, NASA is focused very much on the first one, which is flags and footprints forever. They're looking at a Mars mission that's very much focused on a throwaway systems, one-offs, spectaculars that are exciting and inspiring, they think. And then you go back and then you throw it all away. Because that's what happened after Apollo. After Apollo landed on the moon, we threw away that system because Apollo's mission had been fulfilled. Instead, to become a true spacefaring species, you need to build a permanent system, space-based, that's extensible, and that actually works over a long period of time to create continuous access to all points in space. So, I think I'll close with this quote from Kraft Erica, and I really think it's a good one, because the moon is incredibly useful. It's a way for us to break the current paradigm of launching everything from the Earth, which is incredibly expensive and incredibly wasteful, simply because we don't know of any other way to do it. So for the first time, we can look at a different way of doing things in space. I'll close. I just want to mention, I can't resist a plug. I've summarized a lot of this work in a book that's coming out this month. It'll be out on the 19th of April, and it's called The Value of the Moon. And I'll be glad to answer any question.
Thank you, Paul. We've got time for maybe 2 quick questions. Someone who hasn't asked one yet, or Nick hasn't asked one yet.
Thanks. Paul, can you say a little bit more about what I call the political side of Mars versus the Moon and the possible change in the American administration that's coming up? Obviously, we don't know what's going to happen, but Charlie Bolden's obviously pretty much committed to Mars.
Well, he says that, yes.
Do you think perhaps in the future beyond Charlie Bolden there could be a change in attitude with
Well,
a different president?
Yeah, yes, I think there will be, simply because the current belief that we're on the way to Mars is simply mistaken. There is no architecture to get there. There's no way fiscally to navigate it. There's no long-term plan to get the technology we need on a timely basis. So it's just a bridge too far in a lot of ways. The reason it's popular is because people look to the only successful program that's achieved something in deep space, and that's Apollo. So they figure the way to go to Mars is with an Apollo template, and I think they're wrong. I don't think we'll ever get there that way. Even the Constellation system, when back in the days when we were using that to go to Mars, the Mars Design Reference Mission, and it had a nuclear thermal rocket, so it reduced the total amount of propellant needed. It still needed 8 to 10 Ares 5 class heavy lift launchers, and most of those were propellant. And that's just not sustainable in anybody's way of looking at things.
Okay, one more question. I'll let James have a quick one.
So, whenever I've presented this kind of topic about mining the moon and using lunar volatiles for exploration to the general public, I always get asked about the ethics of doing so,
Right.
and whether or not it's justifiable. How would you answer these questions?
Well, I look upon it as a question of how much are we going to actually change the moon? How much are we going to take versus how much is there? And effectively, I look at the moon as a way to bootstrap our way into a permanent presence in space. I did the calculation once based on the amount of ice at the North Pole. How much water is there? Because I get asked the question, are we going to run out of water? It's a finite resource. You're going to use it all up. And I say, well, there is at the rate that it's there, we could launch the equivalent of a space shuttle every day for 2,200 years. So it would take a long, long time for us to really make even a serious dent in the water inventory. So yes, I certainly agree we're changing the solar system, but I also look at that as sort of inevitable. Where people have gone, they have changed things. Mankind always rearranges his environment to suit his needs. So the really question is, are you going to do it in an intelligent manner or are you going to do it in a careless manner?
Okay, thank you. I think we have to move on. Thank